In Chapter 9, Part 1, Molecular Shapes, we're going to begin to look at how do we draw a molecule in 3D. So Lewis dot structures tell us about how a molecule is connected, but doesn't tell us how it's arranged in 3D space. So if we think about CCl4 or carbon tetrachloride, the number of valence electrons is 4 plus 4 times 7, which equals 32. So we could draw a structure, and we will, where we connect all of the chlorines to the carbon via single bonds at 90 degrees. We're going to use up our lone pairs, and so once I finish drawing these on there, what we'll notice is we've used all of our molecules, but all of our chlorine atoms are approximately 90 degrees apart. So this angle here is 90 degrees. But it turns out that this molecule is flat, and so if we want our chlorine atoms to be as far apart as possible, 90 degrees in a two-dimensional space isn't as far apart as possible. So we could imagine a way to draw this in three-dimensional space where all of our chlorines are now 109.5 degrees apart. I know, lone pairs take forever. So now this angle here is 109.5, and so is the angle in all of the different places between any of the chlorines. So as we start to think about 3D space, we want all of the atoms to be as far apart as possible. Now, you'll notice that I drew a structure with these weird triangles and these dashes. So let's think about what that means. In this case, we have carbon, and then we have a bond going up and one coming out at the side. This angle here is approximately 109.5 degrees. I don't use a protractor, and so it just needs to be close. So these two, and then we used a wedge, and then dashes. So what does all of this mean? So this line and this line are in the plane of the paper. Now, this piece here is called a wedge, and this means coming out of the paper. And so it means that it is in front of the paper, kind of pointing towards you. These dashes at the back are behind the paper, or the board that you're looking at. You could rotate this molecule in many different ways in order to see what these look like in 3D space. So when we draw this, the wedge means that it's coming out of the paper, the dashes are behind, and the two solid lines are basically in the plane of the paper. So in this section, we're going to learn how to draw these molecules in 3D space. So as we think about this, there are a couple of other things that might be important. So for wedges, I tend to draw mine like this. I have also seen them, that's not what I was looking for. Oh my goodness. It's where they look like this. They do not look like a solid square line, but you basically need a triangle. You can fill it in or not. For the dashes, mine tend to all be in the same size. Some people do theirs to where they get bigger as they go out, and other people get smaller as they go out. And even when I tried to make mine bigger, they really all just look about the same size. But it can look anything like that. Approximately all of these angles should be about 109.5. The wedge tends to go in front, but the important part here is these angles are not 90 degrees. So this is not what you can draw. So that doesn't show any 3D structure. So this is wrong. you need to show some dimensionality. So you should have one going up, one coming out to the side, and then a wedge and a dash that look roughly the same. So in the next several minutes, we're going to look at all of the different ways that we can create molecules. So what we're going to draw is the valence shell electron repulsion model, VSEPR repulsion model. So VSEPR. This is a 3D structure. And so we're going to make these 3D shapes. And so it's important that you, at the end of the day, you need to know, aka memorize, the bond angle, what we're going to know as the molecular geometry, and the electron geometry. And so over the next several slides, we're going to begin to think about all those things. But before we can do that, we want to talk about the molecular geometry types, basically give ourselves some version of a reference point. So there are electron domain geometries and the molecular shape. So these are two different things that basically tell us what is this going to look like. So the electron domain geometry, there are 5 of these. And these are all determined by the steric number. I tend to abbreviate this as SN, which just stands for steric number. And that is the number of things connected to the central atom. And these could be atoms or lone pairs. And so it's the number of things connected to the central atom. So the difference between the electron domain geometry and the molecular shape is that the molecular shape is named after what we can see. So what you can see is the atoms, not the lone pairs. So as we get through most of these, we'll begin to kind of think about what they are. So a lone pair of electrons are these 2 dots, and then we have bonding pairs, or basically just bonds. And both of these are part of the molecules that we see. So we're going to start from the largest steric numbers and work our way down. And so as we think about this, we want to make sure that we are paying attention to the types of whether it is electrons or lone pairs being connected. So the first electron domain that we're going to talk about is octahedral. So all of these are a steric number of 6. So in this case, we're going to start with AX6, where A is our central atom connected by 6 things. And these 6 objects, which are just labeled X as a generic element, are separated each one by 90 degrees. So these are all 90 degrees. So if we were to think about this, there are 6 bonded atoms, 0 lone pairs. And so when we think about this as a molecular shape, the molecular shape and the electron geometry are the same. So the EG is octahedral, and the molecular geometry is also octahedral. So for the first compound in any of these groups, there are no electrons on the central atom. So the steric number of 6 is our ability to just count each of these bonds, which I'm going to highlight 1, 2, 3, 4, 5, 6. So once we do this, we have a steric number of 6. So let's look at AX5E. We have our A central atom. We have our 6 compounds, or our 6 components. One of these is going to be a lone pair. So it turns out that lone pairs take up more space. electrons don't want to be tied into one another. So they're going to force all of the other elements to be a little bit different. So we're going to put those on the bottom. My lone pairs down here. And so what we're going to see is that all of my bond angles here are slightly less than 90 degrees. So we have a lone pair at the bottom, and then we have these four. So if we were to think about this, the bonded atoms is 5. Lone pairs is 1. So then the electron geometry, because there are 6 things connected to this A, is still going to be octahedral. However, in this case, we cannot observe this lone pair down here. So this lone pair, if you were to cover it up, is going to make it look kind of like we have a square pyramid. And a square pyramid, if you cannot visualize that, is something where I'm not the best artist, as you guys probably are learning. It looks something like this. So the molecular geometry is a square pyramid. And so the bond angles is less than 90 degrees. And so we can see that this is something similar to AX6, but in this case, we have one less atom. So let's look at the next one. Now we have AX4E2. We're going to put our central atom, and all of our steric numbers of 6 are going to start with the same base structure. And so at the end of this video, we're going to talk about how to use this. First, we're just going to talk about the shapes. Then we're going to talk about how to use the shapes. So for AX4E2, we have 4 atoms and 2 lone pairs. The lone pairs want to be as far apart from one another as possible. So I'm going to put them on what's called the axial coordinates. And then we have these 2 here, or these 4 here. So these are what we call axial, and these x's are in the equatorial plane. And so now we have bonded atoms, 4, lone pairs, 2. The electron geometry, like everything else, is octahedral. And the molecular geometry is square planar. And these bond angles are 90. In this case, they're exactly 90. Now, you could have also put the lone pairs in another location. So I will draw that for you. You could have also put your lone pairs on perhaps this component. And so if you did this, you could create, this is the same thing as above. It's just a different orientation. So all of these molecules you would be able to pick up and manipulate in 3D space. So that's what this is thinking about. So let's think about the next one. If we have AX3E3. So we have our central A atom. We're going to connect or draw all of our lines. So now we need them to be as far apart as humanly possible. So I'm going to put 2 on the equatorial plane, on the axial plane, and 1 on the equatorial, and the others will be lone pairs. So you are required to show all of your lone pairs, and the lone pairs on the central atom must have 3 dimensions. So they're not just stuck on the central atom, they should be away with wedges, dashes, or lines. So there are 3 bonded atoms, 3 lone pairs. So the electron domain is still octahedral. And the molecular geometry in this case is something called T-shaped. If you were to just erase the electrons, what you would see would be this. And so this is a T-shaped type thing. And so we can see that this is what we're looking for. So the bond angle in this case is slightly less than 90 degrees. So less than 90 degrees. Because this, so it's a little bit less because the lone pairs are going to take up a little bit of space. So our next is AX2E4. So we have our central element. And now the question becomes, where should we put our atoms so that the lone pairs get the most space? So we're going to put our two elements on the top and the bottom. And we're going to have our lone pairs out here. So we can see that there are two bonded atoms and 4 lone pairs. So the electron geometry is still octahedral. So all of them where the steric number of 6 is observed are the electron geometry of octahedral. The molecular geometry in this case is linear because we have A, X, X. And we can see that this bond angle is 180 degrees. And so if we look at all of these together, just a little bit hard to see, hold. So we can see that we start with 6 bonded atoms, and as we go down, we increase the number of lone pairs. And so each of these are just different variations of one another, but the base of all of them is the octahedral structure. So the next geometry we want to think about is the steric number of 5. So if we start with this, we're going to start with the AX5. And so if you were to try to use some toothpicks and other compounds to create this, the structure you would find to give everyone the furthest apart would be to put 2 along the axial, which is the up and down, and 3 along the equatorial plane to where we have these. So in this case, we have a 90-degree angle and 120 degrees. So now there's more than one bond angle, and these bond angles are slightly different. So there are 5 bonded atoms and 0 lone pairs. The electron geometry is trigonal bipyramid. Some people say trigonal bipyramidal. You may put either one, they are both equally correct. And the molecular geometry is trigonal. And so in this case, your angles are 90 degrees and 120. So now we're going to do the same thing where we successively remove one atom and replace it with a lone pair at a time. So now let's look at the AX4E. So we're going to start with the same basic structure. And one of these is going to become a lone pair. And so we're going to place it here because if we placed it on the axial, it would only be 90 degrees here. And so we want it to be further apart than that. And so we're going to put our X's on the axial and 2 of them on the equatorial plane to where our bond angles in this case are slightly less than 90 and slightly less than 120. And so we can see that these lone pairs are basically squashing everything just a little. It's not a significant squish, it's just a slight squish. So in this case, we have 4 bonded atoms and 1 lone pair. The electron geometry is trigonal bipyramidal. And the molecular geometry is something called seesaw. So let's redraw this in such a way that makes a little bit more sense. If we tilt it on its side and remove the lone pair, we can see that it kind of looks like a seesaw. Not the best, but our bonds in this case, we'll just call that bond, is less than 90 and less than 120. So this would be the seesaw molecular geometry. So next we're going to look at AX3E2. We're going to set up our same structure. And now the question becomes, where should we put our lone pairs to give them the most space, as well as not force all of our atoms to be too close to one another? So in this case, we're going to put our lone pairs here and put our three elements here to where they are approximately 90 degrees and these are 120 degrees apart. So we have 3 bonded atoms, two lone pairs. The electron geometry is still trigonal bipyramid. And this molecular geometry might look similar because it's also T-shape. So if you remember back to the steric number of 6, we also had one that looked like this. So we often see the same shape, but the difference here is the number of lone pairs. And so our bond angles in this case are going to be slightly less than 90 degrees. So now let's look at AX2E3. So we have A and all of these. So we want our atoms to be the furthest apart, and we're going to put them here. And we're going to put our 3 lone pairs here in the center. And so we have 2 bonded atoms. Three lone pairs. So the electron geometry is still going to be trigonal bipyramid. And the molecular geometry in this case is linear. And so that looks like this if we've eliminated all of the lone pairs. And so our angles in this case are 180 degrees. So if we look at these, we can see that successively we exchanged one atom for a lone pair, where there are always 5 things connected to the central atom. And in this case, the bond angles are all slightly similar as we think about all of these. So let's think about something with a steric number of 4. So these are called tetrahedrals. So if we have AX4, we've seen this one at the very beginning of this video, where we have A in the center, and our 4 components separated as far as possible, which is 109 or 109.5 degrees. So we have 109 degrees between each of these. So there are 4 bonded atoms, 0 lone pairs. There is the electron geometry is tetrahedral. And in this case, the molecular geometry is also tetrahedral. And our angle is 109 or 109.5. Both of those in this case are equally correct. So now we're going to do the same thing we've done for the other steric numbers, where we swap out a single element for a lone pair until we're all the way down to the end. So in this case, we now have AX3E. So our structure always looks the same. Now the question is, we're going to put our X's here, and our singular lone pair will be up here at the top. So there are 3 bonded atoms, 1 lone pair. And so when we look at these are all going to be slightly different. These are going to be less than 109, approximately 107. So the electron geometry in this case is tetrahedral, but the molecular geometry in this case is a trigonal pyramid. And so if you just have you could kind of imagine that this looks something, if I was a little bit better of an artist, but you can kind of see that it looks like this. Actually, I'm a terrible artist, but you get the idea. So in this case, our angles are less than 109 or approximately 107. And so this squishing, again, occurs to the lone pairs. So sometimes people draw lone pairs with like big balloons over them to kind of indicate that they are being squished. So next, we're going to look at AX2E2. We're going to end up with our same starting structure that looks like this, where we have 2 elements and 2 lone pairs. So I'm going to put my lone pairs here and put my X's here. You could have put them on any one of these. So the other way people draw this is a slightly different orientation, which I myself will use quite frequently. But these are the same, they're just rotated in your perspective. So there are 2 bonded atoms, 2 lone pairs, and so the electron geometry here is considered to be tetrahedral, and the molecular geometry is bent. So if you were to just look at the picture of AXA, this right here is much less than 109.5. So it's approximately 105. And so in this case, for our bent structures, the angle is much less than 109 or 105. And so then if we look at our last one of AXE3, this one looks a little bit different, and we don't tend to observe it all that often. You end up with an A with a singular X and 3 lone pairs. And so we have 3 bonded atoms, we have 1 bonded atom, 3 lone pairs. The electron geometry is tetrahedral, and the molecular geometry in this case is linear. Although we don't tend to think about the AX being a linear component. So now we are trigonal planar, or a steric number of 3. So we're going to start with AX3. And if you have 3 things connected to a center point, the furthest they can be apart is 120 degrees. So in this case, they're 120 degrees, but all in the plane of the paper. And so this is true regardless of how you orient this. So we have 3 bonded atoms, 0 lone pairs. The electron geometry is trigonal planar. The molecular geometry is also trigonal planar. And your angle is 120 degrees. Now we're going to do the same thing where we're going to remove one of our atoms, so AX2E. And like all of the others, our starting material or our starting orientation looks the same. So you could have oriented this in any place where the lone pair was on any of these. So our bond angle here is going to be less than 120 because our lone pair is going to squish them just a touch. And so we have 2 bonded atoms. We have 1 lone pair. We have an electron geometry of trigonal planar. And a molecular geometry of bent. And our angle is less than 120 degrees. So it turns out that the AXE2 does not exist. So there are other components where you could see something similar, but we don't really encounter that structure in Gen Chem 1. But what you can see here is that we've done the same successive removal of compounds. And so again, I didn't use a protractor. You can kind of see that my angles are just close to 120. So this would definitely not be 120. Anything where they're pretty close is good enough. So linear, a steric number of 2. We're going to start with AX2. We have A connected to 2 X's. They're 180 degrees apart. So we have 2 bonded atoms. And 0 lone pairs. The molecular geometry and the electron geometry are both linear. And they are 180 degrees apart. So we don't necessarily see the AX with a lone pair, which would be AXE. So that doesn't exist. But we have seen in some of the other steric numbers where we can have an AX linear bond with additional numbers of lone pairs. So those are the 5 different steric numbers and the different electron or the different molecular geometries that are fit in each one. So the idea is that with that information, we can draw a molecular structure. So here's how we do that. We're going to draw the Lewis dot structure of the molecule or the ion. We're going to count the number of domains or stuff connected to the central atom. Remember, it could be bonds or lone pairs. We're going to determine the electron or the base geometry. So it could only be, or I've also called this the steric number. And so then we're going to use the arrangement of the bonded atoms to determine the molecular geometry. So let's work some examples. So we have these 4 examples. And so what we're going to do is we're just going to start. Let's look at XeF2. So the valence electrons here are 8 plus 2 times 7, which is 22. So following the rules, we're going to place Xe in the center, put our F's on the outside, draw our lone pairs. So now we've used 16 of our electrons. So then we're going to have 1, 2, 3, 4, 18, 20, 22. So we have how many things are connected to our central atom? We have 1, 2, 3 lone pairs. And then we have 2 bonded, 2 atoms. And so in this case, we're going to have a steric number of 5. So we know that this is going to place Xe in the center, and it's going to look something like this. And so from here, we can put our fluorine atoms on the axial positions with their lone pairs. And then we're going to have our 3 lone pairs around the center. So the electron geometry in this case is trigonal bipyramid. And the molecular geometry is linear. So we started by determining the Lewis dot structure and went accordingly. So next, let's look at NH3. So the valence electrons is 5 plus 3 times 1, which is 8. So we know that we're going to get nitrogen with our 3 hydrogens using 6 of our electrons. That will be the last one. So when we count these up, we can count 1, 2, 3 atoms and 1 lone pair. So we know that this is going to give us a steric number of 4. So we can come over here and draw that structure with nitrogen in the center. And again, you could put your lone pair on any of these. I'm going to just put mine on the top. So we have our 3 hydrogens that don't have any lone pairs. The electron geometry here is tetrahedral. The molecular geometry in this case is trigonal pyramid. So now what's our next example? I'm basically going to move these down so that we have a little bit more space. So we're going to have SF6 with sulfur as our central atom. The valence electrons in this case is 6 plus 7 times 6, which is 48. So now we're going to plop sulfur in the center. We're going to connect it to each of our fluorines. And so now we're going to put in all of our lone pairs. And so once we've done this, it turns out that we've actually used all of our electrons. So now we can go in and determine the number of atoms that are bonded here. So we have 1, 2, 3, 4, 5, 6, which tells us that we have 6 atoms, which gives me a steric number of 6 because there are 0 lone pairs. And so now we can draw our sulfur in the center. The base geometry of a steric number of 6 is octahedral, where everything is 90 degrees apart. So then we can draw all of our fluorine atoms and then add in the what feels like 9 million lone pairs. But what you can see here is that we're able to draw a structure that looks significantly more advanced in comparison to the Lewis dot structure. So in this case, the electron geometry is octahedral. And the molecular geometry is also octahedral. So our last example is CH2Cl2. So our valence electrons in this case are 4 plus 2 times 1 plus 2 times 7, which equals 20. So we're going to put our carbon in the center. We have 2 hydrogens, we have 2 chlorines. We're going to use the remaining for this. Everyone has octet. This is a good structure. From here, we're going to determine that there are 4 bonded atoms, so 4 atoms connected, 0 lone pairs, which gives us a steric number of 4. So we know that the steric number of 4 has a base geometry of tetrahedral, which is 109.5 degrees apart. So we have 2 hydrogens and 2 chlorines. And these 4 atoms could have been placed anywhere on here, and so the electron geometry is tetrahedral. And the molecular geometry is also tetrahedral. So the more of these you draw, the easier it is to follow along. But we start by drawing our Lewis dot structure and then determining the steric number. The steric number tells you what the electron geometry is, how many things are connected to the central atom. From there, you want to put the lone pairs as far apart as possible. Then we can determine the molecular geometry based on what we see.